Good morning, and it's a great pleasure to be here. Kim and I think Tracy and quite a few of us, we started this the Stewardship Science Graduate Fellow Program, and it's such a pleasure to see the growth and maturation of the program as well as all of you. And as Sarah talked about yesterday, quite a few of you have really been into our family now as a strong scientist and hopefully emerging leader for the program. So really looking forward to continue working with you guys. Actually, Kim and I go back a long way. I still remember we worked on Nova and Omega experiments together, and I was designing and she did all the experiment, and she was the lead author on the paper that we published together. So we've been in the HED world for many years. So today I want to talk a little bit about stockpile stewardship and high energy density physics. And you guys had the chance to tour the labs and saw NIF. And NIF is just a culmination of many years of effort that now we actually start maturing and delivering some of the data. And if we want to start thinking about stockpile stewardship, actually it started in the mid-90s. In 1992, when United States, when we finished the last underground nuclear test, at that time it was very much in the transition of a lot of uncertainty. And it was through the guidance and leadership of Vic Reese, whom I had the pleasure to work for, and I think Kim as well, on the Vic's Science Council, that we started the Stockpile Stewardship Program. That's really evolved from a test space into a more science space. And that was a major transition that allowed us to maintain the safety, security, and performance of the stockpile such that we can maintain the nuclear deterrence. And a lot of people always thinking about, nuclear weapon. What a terrible instrument of the war. Reality is that many of us, the way we think about it, we don't think about nuclear weapon as an instrument of war, but we'd rather think about an instrument for peace. We're here for deterrence. Our mission is to make sure that the Stockpile Stewardship Program is so strong that we would deter all our adversary to go against the United States or our ally. So that's our focus. And with our underground tests, the role of science and technology continued to mature, evolve, and that actually become part of our strong deterrence effort for the nation because of our strength in science and technology. And HED is an element of that. So to maintain deterrence, we have several missions in mind, right? We want to use science, technology, engineering to validate the physics model. So we don't just blindly trust what our calculation tells us. We want to really understand what's the underpinning physics, and that allowed us to support our stockpile through improving and modernizing assessment of our U.S. stockpile, both the current stockpile as well as the future stockpile that's evolved both through age and modification. We also face adversary that continue to advance to challenge the strength and the position of the United States. So we need to anticipate and respond to these potential surprises such that we will not be caught off guard. And finally, many of us are really, I had the pleasure of doing 3 underground tests in my career, but many of us are on the way out. And really is the focus of future, as you guys also heard from Richard Ward when he gave you the talk a couple of days ago at Livermore, it's really the people that matter, right? It's really not just a tool, but it's really having the expertise to have the true understanding to deliver the confidence. So recruit, train, and retain world-class, a lot of you guys, next generation steward, is a central focus of the Stockpile Stewardship Program. In fact, when Vic Reese started to advocate for the Stockpile Stewardship Program, that was actually the centerpiece that he used to advocate why we need to have a strong science-based Stockpile Stewardship Program. It's the people. It's the people that matters. So this is about as much as I can tell you about what a weapon looks like, okay? So I can tell you the majority of the yield of our current nuclear weapon occur in the high energy density regime, therefore the high energy physics research that we really focus on, are interested in, okay? And in many ways, is the HED facility that allows access into this interesting, challenging physics regime that allows to deliver the data understanding that's important. So this is what a weapon, as much as I can say, what it looks like. It has a high explosive phase where we use high explosive to create a supercritical assembly, this first stage, what we call primary. And in this stage, we're going to do a lot of the experiment using hydro tests, HE-driven hydro tests. We have facility like dual axis radiographic capability machine over there in Los Alamos, Jasper, which is a gas gun in Nevada. We do a lot of these HE-driven experiments to understand the physics in this phase. Then evolve into the HED phase where it becomes higher pressure, higher density, increasing rate, then becomes a primary when the supercritical assembly that generate the first primary energy production. And then we transfer the energy from the primary to secondary, what in the stage we call energy transfer, where the X-ray from the primary is contained and transferred to the secondary stage. And then the secondary phase produces the energy that actually delivered the military effective yield for the US stockpile. Okay? So that's what the secondary produces, the final energy through explosion, radiation. And this is sort of like the rough draw line. This is where it enters from the HE phase into a high energy density phase where we really have to demonstrate that scientifically we're far superior. And right now, I would say that US is the #1 leader in the world in this area. So what we that already talked about, the mission is really focusing on sustaining our current stockpile, enable the future stockpile, and then maintain the capability for long-term stockpile sustainment. And experiments that we do are critical in developing and maintaining the design, and the key were innovation culture for weapon program in the absence of underground tests. And innovation is really important when you have to think about how we develop the weapon. You know, back in the very early days, it really requires the innovation from the Manhattan days all the way to when we start developing the modern stockpile. And these stockpiles are really, we're standing on the shoulder of giants, that they have the intuition to develop these in the absence of a lot of these complicated calculation that we are unable to do today. It's built on innovation and testing that evolved to today's stockpile design the way we have. Okay? And so if you think back in when we did the underground test day and all the way through the early 90s, the calculation is based on so-called supercomputer that the chip is probably far inferior than what we have in the iPhone today. Okay? And the code is crude, but we have a lot of the experiment to help us to parameterize, underpin a lot of the assessment. So we really do have to make a lot of approximation in leading up to trying to assess this very complicated weapon overall. But now without underground tests, what we have to do is start dissecting a lot of these different physics issue approximation that we made and trying to understand what is the physics underpinning. So the evolution now is going from the underground test base now into more of a science underpinning for the future assessment. So experiments are critical. We can't really just count on doing calculation and trust these calculations. We got to meet Mother Nature face on. And all the days of that we have been doing experiment, we have certainly learned a lot of the painful challenges that Mother Nature is oftentimes unkind to us. And we are scratching our head to trying to figure out what is she trying to tell us. And actually, that's often the most challenging and fun aspect of doing our work, is really looking at these unknowns and trying to understand the physics behind it, design the right experiment, getting the right data, and then really solve a problem. And over the last 20 plus years of stockpile stewardship, I say we have some successes and we definitely have some failures. And the successes have really led to some of the breakthrough that we no longer rely on some of the underground approximation, that we actually understand the true physics behind it. And those are true major breakthrough. And that's what stockpile stewardship is all about. And these stewardship efforts really focusing on delivering data platform. And these are not something you can crank out overnight. Okay? So I just use this as a rough illustration of that we ultimately, naturally, we'll focus on data. and you guys were a NIF, there's a Z, and there's omega. And it's these large-scale machines, eventually Z and NIF, that deliver the ultimate data that we use to validate some of our simulations. And they are built on the people, stewards. As many of you know, to get a PhD, 5+ years before you get there, right? It takes many years of our investment to bring these people up. And then even after you receive a PhD, it takes quite a few years for the train to really become a true stockpile steward, to have the understanding, the underpinning, the breadth, the depth that you need to become the expert to make the evaluation. People, platform. Developing a platform takes a long time. It's not something that you dream up and just do an experiment. And many times when we do more complicated experiment, if what you'll see is that we have from initial concept, then we do some testing. For example, oftentimes we'll take some innovative idea to omega to try something out. And then we try many different iterations before we start homing in on this is the right platform, the right diagnostic, the right design. And then we transition and scale up to a larger machine like Z or NIF. And scaling is not easy. And oftentimes we think that works in one machine doesn't necessarily work in the other machine. So it takes more time to develop that platform. Developing a platform into maturation data takes a decade. That's a decade-long effort. It takes a lot of persistence, a lot of investment, a lot of prioritization, a lot of vision to us to really develop the platform. And associated with the platform, all the diagnostic development. And we require more precision, and require data at both precision, but also spatially, spectrally, temporally. So a lot of the diagnostics are critical in getting us the right data that we need. So what I want to do for the rest of the talk is give you an overview of the physics that we use these platforms to develop and why that's so important for stockpile stewardship. So we've been developing a sort of a longer-term plan. So I guess 5 years is about as far as we can see in terms of what we plan to do in the near term. So if you think back to the weapon diagram where I go from primary to secondary, we start thinking about what are the physics that's important to underpin each of the area. So in that planning, what we did is that we start separating into the major key physics topic that's important. And actually, if you look at the Stockpile Stewardship Graduate Fellow Program, where we start focusing on HED, material, nuclear, you will see element view in each one of these physics and why that's important, okay? So we're definitely very much interested in thermonuclear burn. DT fusion is a critical element in order to getting us to the significant yield for the nuclear weapon. So in the absence of underground tests, the only form that we can generate sufficient amount of DT neutron will be in the laboratory, hopefully one day in the ignited platform. So what we do, focusing on, we have developed a number of near-term milestones that we're trying to getting the path to delivering a thermonuclear burning plasma platform. And the very near, this is actually a significant date that we have established, is that we want to determine the efficacy of NIF, whether ignition or credible scaling can leading up to one day toward ignition. And this is applicable for the multiple fusion approaches, and I'll talk in more detail about them shortly. And then leading up to that, eventually leading up to a review where the investment we're going to do for more modern requirement. But we talk a lot about if we get the yield, with higher yield, what can we do beyond ignition? We talk about how to improve it through coupling to getting more fusion yield. And we start planning is that as we get burning plasma platform, what can we do to inform this physics we call primary boost? So these are the thermonuclear burn area that we're really focusing on. Every calculation requires very accurate, validated material and plasma property. If you don't have the right property, it's garbage in, garbage out. Okay? So you really have to count on that we actually deliver the credible materials and plasma property for the material that we care a great deal about. We actually have a near-term milestone. We have life extension program. You see that as the weapon gets evolved, you will see this term for Stockpile Stewardship Life Extension Program. And that's to extend the life of our current stockpile for the longer sustainable future, such that we can maintain the performance and safety of the stockpile. So, but then a lot of material have aged, and it's to the point that, and then all due to environmental safety and health concern, that you can't actually manufacture anymore. So there is an effort that we're going on right now, is that if there's the material that's underground tested, what is a suitable replacement material that we can use without sacrificing the performance? So we're actually delivering some of the data on NIF today to support this weapon system called W80. So -4 is the moderation, fourth iteration of this weapon. That so this will, if we can deliver this, then we don't have to think about doing a much more expensive way to reproduce this material that's being underground tested. Plutonium is probably the most complicated material we have, and it is aging. And then we are talking about remanufacturing of the new plutonium. So supporting plutonium aging and manufacture assessment with many different cross-platforms on Z, NIF, et al. Is a critical deliverable that we're trying to do, and this was the 2024 timeframe. And I'll talk a little bit about opacity. This is truly a lesson learned for us, but I'll talk in more detail. But what happened is that we, a lot of time using plasma opacity based on theory, and for a long time we have strong confidence that we thought the theory is correct, until someone named Jim Bailey had to do an experiment on Z. And that was eye-opening to tell us, oops, we have a strong disagreement. And reality is that at first we all thought, Jim, you did the experiment wrong. This data couldn't be right, right? Well, unfortunately, Jim was a very good scientist, and through a lot of the detailed work, it really shows that the data was credible and the theory is wrong, or could be off, and we're desperately trying to figure out what caused that discrepancy. And so this really tells us that sometimes, don't count on your calculation. You got to do the experiment. And then finally, output survivable, radiation, hydros, and transport. This is the stage we talk a lot about the energy transfer between primary, secondary. So there's a lot of challenging physics associated with that in a very complicated condition. And also the hydrodynamic behavior, where a lot of instability can happen in the different stages. That in terms of radiant hydro and radiation transport are the strong area that we put a lot of effort into trying to understand. And finally, trying to understand the output survivability. This is where we face the threat of our adversary to trying to defeat our weapon as they launch. So we're trying to understand what the impact of various potential threat is, from thermomechanical shock to the system-generated EMP to looking at neutron irradiation, how our component will respond under the threat environment. So what you see here, in a way, is an integrated plan that we're trying to pull together to trying to address stockpile stewardship in these relevant physics. So I will try to go through a bit of detail on each one of those. So first, thermonuclear burn, fusion. You guys visited NIF. We got some expert in the audience, Nathan, that has been really focusing on trying to develop initial confinement fusion. And simply, we're trying to just compress and confine deuterium and tritium into a point that they can reach criticality and eventually sustain burn by containing the alpha energy such that we can achieve the thermonuclear burn condition through ignition. It's a very complicated problem trying to reach convergence to that ratio and get the fuel to be hot enough and to able to confine the alpha. And so these are the challenging physics that we deal with. And we are approaching through a number of different approaches. NIF is really focusing a lot of energy on laser indirect drive using a hull ROM to implode the capsule. You guys seen a lot of that in the visit at NIF. Using direct drive, ignoring trying to bypass the hull ROM, potentially you can use laser to directly ablate the capsule. Rochester has been really the champion to focus a lot on laser direct drive. We are doing some of the experiments on NIF to look at some of these aspects as well. And so this is using direct drive. And Sandia has been the champion looking at magnetic direct drive on Z. So all three approaches by United States are going on simultaneously and trying to achieve the fusion condition or a thermonuclear burn condition that we can use for stockpile stewardship. So why do we want to do that, right? First of all, ignition is the gateway to this laboratory yield that enables direct access to weapon-relevant condition. The DT fusion condition mirrors a lot of things that are going on in a weapon. So when we're achieving different yield, we have determined that at different yield level, we can deliver certain aspect of physics that we care a great deal about for the stockpile stewardship perspective. So from understanding burn in combination with mixing and to even actually right now, NIF is actually probably one of the foremost platforms that we can use for nuclear physics study. Okay. We generate significant amount of DT neutron coming out, and potentially we can actually think about, we can actually use, if you do the right condition, which we are developing, we can actually put material in near a hot plasma, so you can actually generate an excited state, a metastable state, for example, and then irradiate it with DT neutron. And that can actually get you into a nuclear reaction that you cannot access traditionally, right? And we are doing some of those work that we have demonstrated that we can actually dope material. We actually done some experiment down Shaughnessy and led the effort to look at actually fission, using uranium-238 fission dope in the capsule, and then capture these fission fragments to help constrain the fission cross-section. And now with that platform being developed, we can actually start using that for other elements, potentially even some of the shorter-lived isotope that radiochemistry might be really important application for. As we start increasing the yield, we're starting to getting more exciting parameter. One day, a few megajoule what we call ignition, but ultimately, in the higher yield, we can really get into the complex condition. We can actually do a lot of threat condition that combine neutrons and X-ray environment. We can actually study a lot of these to drive material property really close to the weapon condition of interest. And so this is an area that the United States has been really focusing on and trying to deliver this thermonuclear burn platform. So what I think Tammy Ma gave you guys a quick overview about the multiple application for NIF, and energy is one, but really the primary funding and primary driver is delivered the thermonuclear burn platform for stockpile stewardship. Material property is critically important, going from low pressure, moderate pressure to high pressure. You can see a lot of you guys do the planetary science all the way to starting to understand the property at the center of stars. So we similarly have a whole bunch of facility that covers the entire gamut of the regime that we care about, leading up to Omega, Z, and NIF, where we can really achieve the high pressure, even some high temperature condition that's relevant to the stockpile stewardship. So at the solid state, modeling primary implosion at these conditions is important, that we care a lot about the phase of the material. We care a lot about the strength of material. Obviously, you guys know, phase matter, strength matter. Carbon between graphite and diamond, same material, different structure, very different behavior. So similar material, if you have a different condition, they can have very different atomic structure, and they give us very different behavior. So we really need to understand the phase diagram that we have to really map it out. And also strength matter, naturally, you know that when you're trying to squeeze something's water versus ice, they'll behave extremely differently. Similarly, trying to understand when the material melt is a critical importance to us. And also, even at the material when it's solid, they can have different strength property as well. And so therefore, that will really impact the compression of the material. So strength really matters. So what we do in the HED world is trying to deliver these validated data in the regime that previously was only access to theory and simulation. Now, for the first time, through a lot of experiments we have done, we can actually acquire data to try and validate these things where previously were just through simulations. And as I said, these take many years. Rick Krause in the audience, he's been doing a lot of the work in trying to understand the phases of the material. And this is where we are today. We're actually doing experiment. And Rick actually has a shot at midnight tonight to do another one of our plutonium experiment, trying to understand the phase. So he actually has to leave today and then probably stay all night to just get this experiment done. I won't be there, Rick. But we started trying to develop the platform, but it started like 2008, 10 years ago, right? And then we did a whole bunch of diagnostic development and trying to understand using various different material. We did 600 or so shots on Omega over the last 10 years, trying to develop this platform. We publish, but then leading up to finally in 2013, 5 years after you started Omega, we started to develop the first platform on NIF using this diagnostic we call TARDIS, where you have a backlighter, then you use that and then a drive for a specific target of interest. And then we have films that's embedded in these housing that we can actually directly measure these lines. And so we have done both material that for interest, both for fundamental science and also for classified material. So these experiments are ongoing in NIF, but it's through a lot of effort on Omega, and we actually will continue to utilize Omega to develop additional new platform that we can understand some of the phases of the material. So this is actually a very important, but it's a decade-long effort and still continuing. This is an experiment we also started on Omega back in 2006. Actually, we're trying to look at solid strength material. So ultimately, this platform is trying to use what we call the ramp compressed platform and trying to look at drive a material that has a certain strength, that has a perturbation, in trying to measure the growth of this due to this drive. And depending on the strength of material, you will see that the growth can significantly vary, and we use this growth factor to validate some of our strength model. And once again, that requires developing a platform, developing a high energy backlighter. So Omega EP was used to develop this backlighter platform. And when you combine them all together, we started doing a lot of tantalum or using the material, surrogate material, to trying to understand the growth factor leading up to some of the experiments on NIF. And we just finished experiment number 5 using the plutonium on NIF recently. So this is, once again, it's a decade-long effort that finally leading up to our first set of data. We are continuing to look at various different other material platform. This is the Gigabar platform. Allison Saunders, our next speaker, actually worked on that. You're probably going to talk a little bit about that. Yeah. So I won't steal her thunder, but the reality is that we use these to try and understand the very high pressure plasma equation state. It's a very challenging platform that we started, and we do a lot of the work on this NIF discovery science and also Omega that leading up into actually getting some of the data of interest. And we're also using, we're developing planar platforms. So this gets to the gigabar range. This gets into maybe potentially up to 100 megabar range at different material. So combination of the platform, both planar and convergent platform, give us these plasma equation of state that we can use for the data to validate it such that we can deliver the equation of state for the assessment. This is the opacity experiment that I talked about that Jim Bailey did. And this was a paper that Jim published in Nature back in 2015. But the bottom line is that when he first did the experiment, I believe in the iron in a certain condition, actually data initially was in agreement, but Jim didn't stop there. He actually decided to go higher temperature, and then he saw that disagreement. He started using a different material at the lower temperature condition, and once again, there was a significant disagreement. And so therefore, the combination of that led us to say we really have to really focus a lot on trying to get the data, but not only in Z. So effort that we're going through now is a national strategy that's developed to first replicate the ion opacity that we do on NIF, but leading up to different materials so we can do a variety we call anchor condition at various different temperature, different material. So now we have a broad-based data to allow us to assess the opacity. Going on to radiant transport, we've done a wide range of experiments as well. And so we use both calorimetry, which we measure the transport energy through a target that I can't tell you too much detail about, that goes see how much transmit from one to another. So we can measure using Dante to measure the energy in versus energy out. We also look at through radiography, how does these features evolve in time. Once again, this was an effort that started in 2000, and then in 2011 is when we finished this first campaign we call Searchlight. It took 10 plus years. Each one of those lines is actually 1 day omega or multiple shots on NIF. So this was a delivery that we have that actually concluded a major campaign on NIF. Then so that was actually one of the first success on NIF for stockpile stewardship. And we'll continue the radiant transport experiment in other more complicated geometry. Hydrodynamic, we're trying to understand the mixed instabilities. So this is a planar reshock experiment where we're actually using NIF to as a one main drive to generate the initial shock, and then using a second drive to time it such that we can actually have a reshock and see how that can change the growth due to Rieckmann-Meshkov instability at various conditions. And this is a single mode. We can see that there's strong agreement between simulation and experiment. What we're actually doing now using a multi-mode, so trying to look at the mode coupling between different wavelengths and how that can react under Rieckmann-Meshkov condition. We have done similar experiment using similar condition to look at shear, Kelvin-Helmholtz instability, as well as Rayleigh-Taylor instability. So we do a gamma of these hydrodynamic experiment. And we also, that's a planar experiment. We also do convergent experiment where it's hard to directly measure a growth factor. So here we're actually using a capsule where in this case we have a CH layer ablator we fill with tritium, and then we can embed different thin layer of CD into the CH layer. And if there's mix, then deuterium and tritium will mix, and through these time of flight neutron spectrum, we can actually start diagnosing the impact of mix. And when you embed a different layer, you can see the extent of the mix. So we use neutron actually as a signal to understand our mix. So finally, output and survivability. We are doing a range of experiments, look at vulnerability hardening experiment. NIF, Z provides sources, X-ray sources, neutron sources, and we also use using that to generate, the system generate EMP. So we have test objects in there to look at it, impact irradiation for both neutron and X-ray, not only in terms of material, but also in terms of electronic components. So we're studying the vulnerability and using that to assess whether we can survive in a hostile environment. Finally, people. Attracting you guys to work on this is critical for long-term sustainment. This is actually a lot of, maybe some of you are in this picture, right? This is the stockpile, there's Laura, and this is the stockpile stewardship. So from the old days, where a lot of people work on the stockpile, many of us are retiring, we need to hand the baton to the next generation. And we need to make sure that you guys are equipped properly through both simulation and experiment, such that we can gain the knowledge and expertise to sustain the stockpile in the foreseeable future. So in summary, I just want to see that the HED and also all the things that you work on are really important to support the current and the future stockpile in the long-term sustainment of the health of the stockpile. And these experiments are critical, and I want to emphasize the word innovation. Without these capabilities, we cannot innovate, and we need to be able to sustain that culture of innovation. Okay, Thank you.